we now discuss how to compute for conditional probability. Conditional probability is defined as the probability of an event given that another event has occurred. In a more specific way, the conditional probability of an event A given B is the probability that event A will occur, given that an event B has already occurred. In other words, if B occurred, then what is the chance of A occurring? As we can view from this graph, event B has already occurred. We also note the probability of B intersection A. Then the probability of A happening conditioned on what B has already occurred. Then the probability of A happening conditioned on that B has already occurred is given by the probability of A intersection B over the probability of B. From the definition, the probability of A conditioned on B is equivalent to calculating the chance of event A happening inside only B, while ignoring the complement of B. Therefore, we have the probability of A conditioned on B is equal to the number of observations in the intersection of A and B over the observation of the entire B sampling space. It's equal to probability of A intersection B over the probability of B. Let us look at this example of George going to San Francisco. We know that whether George will go to San Francisco tomorrow depending on the weather condition. Regardless of the weather condition, suppose the chance that George will go to San Francisco, denoted by G, is 0.48. We note that the chance that the weather in San Francisco will be nice tomorrow, denoted by S, is 70%. And the chance for George to go to San Francisco and the weather is nice at the same time is 36%. Then, given that the weather will be nice tomorrow, what is the chance that George goes to San Francisco? Using the conditional probability equation, it is not hard to get probability of G conditional on S is equal to probability of G intersection S divided by probability of S, which is equal to 0.36 divided by 0.7 equal to 0.5143. So overall, the chance for George to go to San Francisco tomorrow is higher if the weather is nice, based on the conditional probability that probability A conditional on B equal to probability of A intersection B over probability B. We may multiply probability of B on both sides of the equation. Then we can easily infer that probability of A intersection B is equal to probability of A conditional on B times probability B. This new equation is called the general multiplication rule. This gives us another way to compute for the probability of intersection. In fact, following the same logic, we can obtain another multiplication rule. That is, probability of A intersection B equal to probability of A times probability of B conditional on A. which is equivalent to the previous equation we obtained. We may choose which multiplication rule to use depending on what property information we have. Now, let's look at this example. A golfer has 12 golf shirts in his closet. Suppose 9 of these shirts are white and the other are blue. He gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not return the shirt to the closet. What is the probability both shirts are white? To do the computation, we may first define W1 as the event that the first shirt is white, and W2 as the second shirt is white event. Given that there are 12 shirts and 9 of them are white, the probability of the first shirt is white is given by 9 over 12. If the first shirt is white, then there are 11 shirts left in the closet in the beginning of the second day. The chance that the second shirt is white too is given by 8 over 11. So using the multiplication rule, we have the probability of both shirts are white is given by the probability of W1 and W2 equal to the probability of W1 times the probability of W2 conditional on W1, which is equal to 9 over 12 times A over 11, which is equal to 0.55. Therefore, the likelihood of selecting 2 shirts and finding them both to be white is 55%. This can be extended to more than 2 events. Based on the multiplication rule, we can then define an independent event. Intuitively, if 2 events A and B are independent of each other, then the probability of A conditional on B should be the same as the probability of A, regardless of what happens to B, because the condition of whether B occurs or not should not matter due to their independence. Similarly, the probability of B conditional on either A or complement of A is equal to the probability of B if A and B are independent. Again, the condition does not matter because the 2 events are independent. Statistically, we can also define that A and B are independent if probability of A intersection B equal to probability A times probability B equal to probability B times probability A. Therefore, to verify whether 2 events are independent, we may plug in data into the last equation to see whether it is satisfied or not. If the equation is satisfied, then the 2 events are independent. To show you how to verify whether 2 events are independent, we can use the case of George going to San Francisco. We already know that the probability of G intersection S is given by 0.36. Multiplying probability of G and probability of S, we have probability G times probability S equal to 0.7 times 0.48 equal to 0.34, which is not equal to 0.36 for the intersection probability. Therefore, whether George goes to San Francisco is not independent of the weather condition in San Francisco. In other words, the weather will certainly affect George's traveling plan, and it is more likely that George will go to San Francisco if the weather is nice. In this video, we have introduced the concept of conditional probability general rule of multiplication, and independence of event. Again, please practice the quizzes with detailed procedure. Good luck. Thank you.